Let's take a look at mathematical induction, which is the last method of proof we will learn about in discrete mathematics. The examples I will go through with you after learning what mathematical induction is all about will all be related to summation formula and inequalities. Mathematical induction is a process that can prove p of x is true for some propositional function. And what it says is this: if I have a ladder, let's pretend I have a ladder that is infinite, which means it goes on forever, which by itself would be pretty cool. What mathematical induction says is first we must prove the basis step. And the basis step says you can get to the first step of the ladder. P of 1 is true. So it's true for the lowest or least element in your set. And we'll talk in the next section about the well-ordering principle and what that means. But for now, just go with it. We're going to verify that, yes, we can get to the first step. Then we have our next step that says, verify that if P of k is true, then P of k plus 1 is true for all k's. And what that means is we're going to write an inductive hypothesis that says, hey, this is P of k, and we're going to assume it's true. And that means that if I can prove that if I can get to this ladder, this rung of the ladder, then I can get to this rung of the ladder, which is P of k plus 1, then essentially what I've proved is that the statement is true for all k's, because what if I made this P of k? Well, then if I can get to the first, which I proved in the basis step, then I can get to the second. And if I can get to the second, then I can get to the third. And if I can get to the third, then I can get to the fourth. And you get the idea. This will go on forever and ever and ever. So this is the idea behind mathematical induction. So let's take a look at the process of mathematical induction with a summation formula we should be familiar with. And that summation formula from chapter 2 says if I add up the integers from 1 to n, then it's equal to n times n plus 1 all over 2. And so all of this is essentially p of n. That's what we're saying, is that's the statement that I'm trying to prove is true. Okay? So what does that tell me? That says the basis step, I have to prove that P of 1 is true. And essentially what that means is I'm going to plug in 1, or just use that one value. So I'm saying 1 equals, does that equal the same as 1 times 1 plus 1 over 2? So again, using this formula. Well, on the right side, I get 1 times 2 divided by 2, which is 1, and therefore P of 1 is true. So this formula does hold true for the value of 1. That brings us then to our inductive step. In our inductive step, we are to assume P of k is true. And then I have to prove that because P of k is true, then P of k plus 1 is true. So how do I do that? I have to start with my inductive hypothesis. And my inductive hypothesis is just a way for me to show P of k is true. And so essentially I'm going to go back to the original and say my inductive hypothesis means 1 plus 2 plus 3 plus blah, 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 all the way up to k, again, because I'm assuming P of k is true, is equal to k times k plus 1 divided by 2. So I'm assuming that is true, and that means I must show that 1 plus 2 plus 3 plus blah, blah, blah plus k plus 1 is in fact equal to k plus 1, k plus 2 divided by 2. Because again, I've added a plus 1 on each of the values in the numerator. So if I can show that's true based on this, then I've proved it. So let's see how we do. So if I have 1, let me change colors again. If I have 1 plus 2 plus blah 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 plus k plus 1, then that is equal to k times k plus 1 divided by 2, which is all of the stuff up to this point, plus k plus 1. Because all I've done essentially is added k plus 1 to each side of my equation, because I already knew that this equation was true, and so all I did was recopy that equation and then add k plus 1 to each side. So on the left side, I'm set because what I have is exactly what I wanted to have, is that I'm going through k plus 1. On the right side, what I'm trying to do is rearrange it a little bit so that I can see, does it in fact equal what I want it to equal? And so let's take a look at writing everything with a denominator of 2. So obviously k and k plus 1 has a denominator of 2. And what I want to do is I want to add, how can I write this as a denominator over 2? Well, I can say 2 times k plus 1 over 2 is the same thing, and so that's what I'm going to do, is I'm going to put 2 times k plus 1, and notice it's all over 2. So let's do a little bit further reduction here. On the left side, I still have the same thing. And on the right side, all I'm doing is I'm looking at basically factoring by grouping here and saying that that is the same as k plus 1 times k plus 2 divided by 2. And that is what I wanted to have happen, and therefore I have shown that if I add 1 plus 2 plus 3 plus all the way up to n, it is equivalent to n times n plus 1 over 2. So in this proof, we are going to use mathematical induction to show that for all non-negative integers n, that 1, which is basically 2 to the 0, plus 2, which is 2 to the first, plus 2 squared, plus 2 to the third, etc., all the way up to 2 to the n, is equal to 2 to the n plus 1 minus 1. And so we're going to do this proof again using induction together. And I'm going to add a step that I didn't show last time. We did talk about it last time, but I'm going to start by saying assume P of n is the proposition that 1 plus 2 plus 2 squared plus blah 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 plus 2 to the n is equal to 2 to the n plus 1 minus 1. So last time we did talk about that. I didn't explicitly, sorry, I had to rewrite that. I didn't explicitly say this statement, but it is a good idea to say that statement because obviously now we're saying this is what our statement is that we are going to prove. So then step 1 is the basis step. And remember, the basis step says prove that the lowest value is true. Now in the last one, that value was 1. But because we're dealing here with all non-negative integers n, we're going to prove that P of 0 is true, because what we really want is we want that least element. And again, we'll get into more detail with that later. But let's go ahead and prove that is true. So I'm going to say P of 0 means that 2 to the 0 is equal to 2 to the 0 plus 1 minus 1. And 2 to the 0 is 1. And 2 to the first is 2. 2 minus 1 is 1. And therefore I have in fact proved that P of 0 is true. So basis step complete. Step 2 is my inductive step. And in that step, I am going to prove if P of k is true, then P of k plus 1 is true. Now keep in mind what that means is I'm going to assume that P of k is true, which means I have to write my inductive hypothesis. And my inductive hypothesis is me basically writing out that P of k is true. So I'm going to assume that 1 plus 2 plus 2 squared plus blah 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 up to 2 to the k, because again I'm dealing with k, is in fact equal to 2 to the k plus 1 minus 1. I'm assuming that is true. Now in your text, typically it's not going to say what are we trying to prove is true, but for me, I like to have that so that I know what's my goal. So I want to show that in fact 1 plus 2 plus 2 squared plus blah 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 plus 2 to the k plus 2 to the k plus 1 is equal to, again I'm adding 1 to k, so this would be equal to 2 to the k plus 2 minus 1. That is my goal. So if I can prove that, then I have shown this by mathematical induction. So I'm going to start with that inductive hypothesis that says 1 plus 2 plus 2 squared plus blah 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 plus 2 to the k, and I'm going to leave a little bit of space, is equal to 2 to the k plus 1 minus 1. And just like I did on the last one, I'm going to then add 2 to the k plus 1 on each side. Now why did I do that? Again, because I knew all of the stuff that I'd written in orange is true, and now I'm just adding something equal on each side. And what I'm trying to get to is, of course, here. So let's see if we can get to that from what I have just written. So on the left side, I have exactly what I want. I have 1 plus 2 plus 2 squared plus blah 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 plus 2 to the k plus 2 to the k plus 1, which is what I wanted. On the right side, what I'm looking at is what if I sort of combined my like terms here? What if I said, well, in fact, I have 2 to the k plus 1s minus 1. Because I do. I have a 2 to the k plus 1 and I have a 2 to the k plus 1. And so really I'm just saying, hey, I've got 2 of those. But we know mathematically, and again, left side isn't changing, but mathematically I know if I'm taking, I've got 2 to a power and I'm taking it times 2 again, essentially I'm just increasing that power by 1. So this is in fact 2 to the k plus 2 minus 1, and therefore I have proved that to be true. So let's take a look at one that's a little bit harder. And this one's harder not because it's a harder proof, but because I haven't given you what to prove. And so if I don't give you what to prove, it's up to you to conjecture what it is that I should be proving and then prove it. So it's really 2 parts. And so this is talking about the sum of the first n positive odd integers. So best idea here is to just start plugging and chugging and seeing if we can see a pattern. So we're going to look at it for n equals 1, for n equals 2, for n equals 3, n equals 4, and can we then justify that for n equals n? So for 1, obviously that just means the sum of 1, which is 1. For 2, that means the first two positive odd integers, so that's 1 plus 3, and 1 plus 3 is 4. For n equals 3, that means 3 integers, 1 plus 3 plus 5, which is 9. For 4, it's 1 plus 3 plus 5 plus 7, which is 16. And what I'm looking at is there a pattern? And this appears to be 1 squared, and 4 is 2 squared, and 3 is 3 squared, or 9, excuse me, is 3 squared. I was looking at this 3. And as we can see, what I'm ending up with down here seems to be n squared, which is fantastic because now I have an idea of what that sum will be. What I also need to look at is how would I write this in terms of n on this side, because remember, I want this to be my statement that the sum of all of these values is equal to n squared. And so I have to look at what would I do with n to find the next integer. So to get 3 from 4, to get 3 from 2, to get 5 from 3, to get 7 from the 4, being that's the next integer that I'm adding, means that I'm actually taking 2 times n, so 2 times 2 would be 4, minus 1 to get 3. 2 times 3 is 6, minus 1 to get 5. 2 times 4 is 8, minus 1 to get 7. So that is my formula. So obviously that part wasn't super easy. This is going to end up being, when I do this on the next page, this is going to be my statement, P of n, is that 1 plus 3 plus 5 plus ... plus 2n minus 1 is equal to n squared. So now that I have come up with, I've conjectured my summation formula, now I want to actually prove it. So now that I've done the work to come up with the formula that I think is right, I actually have to prove it. And so again, I'm going to start by just explicitly saying that P of n be the proposition that 1 plus 3 plus 5, etc., all the way up to 2n minus 1 is equal to n squared. So I'm just explicitly saying that is true. And then I need to show my basis step. And remember, my basis step just is looking at the lowest value. And so if we're looking at this, we really started with n being a positive integer. And so that my basis step would be the lowest positive integer. So I have to prove that P of 1 is true. And what I can do then is say, well, that would be 1 equals 1 squared. And is that true? Yes, 1 equals 1. Therefore, the basis step is proven. We'll do it that way. 1 equals 1. The next step is the induction step, or the inductive step. And remember, that says assume P of k is true, show P of k plus 1 is true. And again, I like to write it out explicitly, and you have to write the inductive hypothesis. And my inductive hypothesis is that 1 plus 3 plus 5, etc., all the way up to 2k minus 1 is equal to k squared, because again, we're looking at P of k being true. Then I want to show, and again, I like to write this step so I know where I'm headed. I want to show that if I continued this and I added the next integer, and so the next integer would be 2 more than 2k minus 1, which would be 2k plus 1. I want to show that if I add that to the left side, then the right side will become k plus 1 squared. So that is what I'm trying to get to, is saying I'm going to add the next odd integer, and I should end up with k plus 1 quantity squared as my solution. So now let's go about doing this. I have 1 plus 3 plus 5 plus blah 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 plus 2k minus 1, which I know is true, and that is equal to k squared, which I know is true. And I also know that if I add something equal to each side, then the equation still holds. So I'm going to add 2k plus 1 to each side of the equation. So I haven't broken any mathematical laws. I've added something equal to each side. Now, on the left side, this is exactly what I wanted. I have the same series or progression that I had before, and all I've done is now add 2k plus 1, which is what I wanted to get to. And on the right side, I'm trying to see if that is in fact equal to k plus 1 quantity squared. And so what I'm looking at is I have three terms, k squared plus 2k plus 1, and it looks like I can factor those. And if I factor, I'm looking for numbers that multiply to 1 that add to 2, which is 1 and 1. So this would actually be k plus 1, k plus 1. And of course that means that everything I have here, 2k minus 1 plus 2k plus 1, is equal to k plus 1 quantity squared because I had two of them. So I have in fact proved that to be true. Now let's switch gears a little bit. We've looked at three different summation proofs using mathematical induction. Let's look at one that involves an inequality that says n is less than 2 to the n. So again, we're going to go about this the same way. We have to start by telling everyone what Pn means. So we're going to let Pn be the proposition that n is less than 2 to the n. So that's where we start. Then we do our basis step. And again, we're dealing with positive integers, which means I'm starting by show that p of 1 is true. And so here I'm going to let n equal 1. So I'm saying 1 is less than 2 to the first, and 2 to the first is 2, and that is true, so the basis step is complete. Then I have to look at the inductive step. And the inductive step says assume p of k is true, and then show p of k plus 1 is true. So I'm going to do my inductive hypothesis, which is essentially me writing that k is less than 2 to the k, because I always just take whatever I'm proving and use k. And so that is what I'm going to assume is true. And remember, in order to show this, then I have to say that pk plus 1 is true. So I'm going to say that if I make it pk plus 1, then it is the same as that being less than 2 to the k plus 1. So essentially just adding 1 to k on each side. So that's my goal. So now I actually have to start with my proof. And remember, to start with my proof, I'm looking at my inductive hypothesis. I'm saying that k is less than 2 to the k. And what I want to do to each side is I want to add 1 and see if I can eventually get to my statement that says show. Now this one is not quite as straightforward as what we've done before, but what I have shown is that 1 is less than or equal to 2 to the k. Now I know that's true because I just looked at 1 and I know that that was true here. So really what I'm going to do is I'm going to replace 1 and say, well, this is now less than or equal to 2 to the k plus 2 to the k. So I've just replaced 1 with 2 to the k. I've rewritten this 2 to the k. And what does that mean? That means it is equal to 2 to the k's, which is equal to 2 to the k plus 1, which is then what I wanted, is k plus 1 is equal, or sorry, is less than 2 to the k plus 1. And so again, we use the assumption that p to the k is true, and then manipulated to show what we wanted to in fact show. And so I have proved that to be true. So let's take a look at another inequality, because obviously these get a little bit trickier. They're not quite as straightforward as the last ones. Here we're proving that 2 to the n is less than n factorial, but notice n is a positive integer greater than or equal to 4, which means when I'm doing my basis step, I have to start at 4 because that's the lowest value. So I'm going to start by saying let p of n be the proposition that 2 to the n is less than n factorial. Then I want to do my basis step, and again, since n starts at 4, I have to show 2 to the 4th is less than 4 factorial. Well, 2 to the 4th is 16. 4 factorial is 4 times 3, which is 12, times 2, which is 24, times 1. 16 is less than 24, so the basis step is complete. I've shown that to be true. Then I'm going to do my inductive step. And remember, my inductive step starts with my inductive hypothesis, which says 2 to the k is less than k factorial. That is what I'm assuming to be true. What I want to show in order to prove this is true is again k plus 1. So I want to show that 2 to the k plus 1 is less than k plus 1 factorial. That's what I want to show. So let's see if I'm able to do that given what I know. I start with 2 to the k is less than k factorial, because that's what I know. So what am I going to do to each side? I'm actually going to multiply it by 2. Now, why do I do that? Because I want my left side to be 2 to the k plus 1. And I know that if I have a base of 2 and I take it times 2, then on the left side what's going to happen is this is going to be 2 to the k plus 1, because I have 2 to the k and 2 to the 1, and that means I can just add those together. So I have 2 to the k plus 1 is less than k factorial times 2. But remember, what I'm trying to get to is k plus 1 factorial. And so how am I going to go about this? Remember, because I'm dealing with inequalities, as long as I replace, say, 2 with something greater than 2, then I haven't broken any laws, because all I'm trying to do is preserve the inequality symbol. And so what I know is that 2 is less than k plus 1. And so I am going to replace, I'm going to keep this left side 2 to the k plus 1. This is still less than. This is now k factorial times k plus 1. So I've preserved that inequality. And what do I know about k factorial times k plus 1? Well, I know that that is actually the same as k plus 1 factorial, just by definition of a factorial function that says if you have k factorial, remember that means k times k minus 1 times k minus 2, etc., all the way down to 2 times 1, etc. And so if I instead add a k plus 1 times all of that, this is actually equal to k plus 1 factorial. And so that is where I wanted to end up, and I have, so I have proven this to be true.